Welcome everybody to Algebra 2, Section 2.4, Solving Systems by Graphing and Substitution. So let's first define what a system of equations is, and that is two or more linear equations. The honors classes will cover 3 linear equations in a system, but the non-honors classes, the regular classes, will only cover two linear equations in a system. Now there's 3 ways to solve systems of equations, and that would be by graphing and substitution for 2 of them like we're covering today. And the third one, which we'll cover in 2.5, is the elimination method. Now when you graph these solutions, you'll see visibly one solution, no solution, or infinitely many solutions. And that would happen regardless of whether you graph it, substitute, or eliminate in order to solve. All 3 would yield the same result on a given problem. But visually, we'll show them here. So one solution just means that you have these 2 lines, or these 2 linear equations, that intersect some way, somehow. And that orange dot would be some x, y coordinate. That would be their answer. Now, where and how these lines intersect doesn't really matter as far as what it has to be or something like that. It's just as long as they intersect, that wherever they intersect is the answer. So maybe they intersect to the top and right, maybe they intersect over here. Wherever they intersect, however they intersect, we don't really care. We just don't know I guess I should say the where we do care about, because that's our answer. Now we said wherever they intersect is our answer, so if there's no solution, that means there's nowhere they intersect. And so if they're not intersecting, that means the lines are parallel. And so parallel lines yield no solution. So I do the little parallel line symbol so we can remember this. The infinite solutions, or infinitely many solutions, just means that these 2 lines are actually very secretly the same exact line with one on top of the other. And this means that they would share every single point that each of them have, thus giving us infinitely many solutions. So I'll write down that this is where they are the same line. Now in order to solve by graphing, we first start by graphing one equation, then we graph the other, and we just figure out where they intersect and write that ordered pair down as our answer. So this first one here, it's in y equals mx plus b form, so we know the m is negative 5/3, and the b is negative 6. So I'll begin with b, which is negative 6. And then my slope is negative, meaning I'm going downhill in some way, some manner. And I gotta go 5 for my rise, 3 for my run, and so I can go up 5, left 3. But if I try going down 5, left 3, I notice I get off the graph. Now I may still have to end up doing that, but we'll see. So I'm going to go up 5, left 3 again, and then I'm going to connect these points. Now notice, it is important that we use straight lines here, and I'll clarify the why as after we do the second graph, or second line on the graph. But for now, I just want to mention, make sure you do have a straight edge in order to make these lines straighter. That's going to help you get your answers correct. Now, the straight edge can be something like a phone even, or a ruler, or a binder, a notebook, or folder, just something that would help us keep it straighter. Let's graph the second line here, the, once again, slope-intercept form. So the m is 1/6, and the b is 5. So I'll begin at 5, and I can go uphill, so I can either go up 1/6. Now notice, this point is getting me farther away from the other line, so it's getting me farther away from where they intersect. You don't necessarily need to graph that point, but if you graph it, it's not wrong either. But the direction I do need to go is down and to the left here, which would be right there. And so as I connect to these points, whether you include the top right one or not, we end up getting our intersection of negative 6, 4. And that's the ordered pair that they both connect at, they both touch at or intersect or cross. And that means that in our equations, if you were to plug in negative 6 for x in each of these equations, that both equations give you positive 4 out. And that's the only point that would work in both equations to get the same result from the same starting point. So for example, there's plenty of numbers that could plug into x and get y out of some number. And same thing in the other equation, but negative 6 is the only number that you can plug into both equations, while both equations get you positive 4. Number 2, y equals 5. That's secretly a slope of 0, because that's y equals 0x plus 5, which is why you don't see any x's there. The b would be 5 here. So I'm going to go up 5. I have a slope of 0, which is, if we recall, a horizontal line. Anytime you have y equals a number, it's always a horizontal line. Our other line, the slope is 2, or 2 over 1, and the b is 7. So I'm going to go up 7. And once again, if I go up into the right here, I'm getting farther away from my other line, so I don't really need to do that. But if I go down and left, I'm getting closer to my other line. I actually cross the other line. And so I can connect these. And once again, if you did go ahead and make the dot up here, that's also perfectly fine. And so where they intersect here is negative 1 comma 5. Now I forgot to mention in the last problem the y behind the straight edge for these for the graphing of these problems. That's because if we don't have a straight edge, then where they intersect could appear slightly off, and then we write down the wrong combination, the wrong order pair. Number 6, on these problems, notice that they are not in slope-intercept form. So we either have to get them in slope-intercept form or solve by using, or graph by using the x and y intercepts. I'm going to go ahead and get them into slope-intercept form by getting y by itself. So in the top equation, I'll subtract 6x to get negative 5y equals negative 6x minus 45. Then dividing everything by negative 5. Y equals positive 6 over 5x plus 9. So the slope is 9. The b is, sorry, try that again. The slope is 6 over 5, and the b, or the y-intercept, is 9. So I'm going to go up 9, and it goes uphill from left to right, 6 over 5. So I'm going to go up, right, 6, up, and then right, or I can go down and then left. So I'm going to go down and left here because that's the only spot I even have room on this graph. I'm going to go ahead and do that again. Down 6 and left 5, and I just barely got it on the graph. Connect these dots, making a straight line, and call it good. On our other equation, we have to get y by itself by subtracting 2x first. So we get 2y equals negative 2x minus 4. So now if I divide everything by 2, I get y equals negative 1x, or negative x minus 2. So the slope is negative 1, or negative 1 over 1, and the b is negative 2. So I'm going to go down 2 to begin, and I'm going to go in a downhill manner up 1 over 1. And so I'd only really need to go up and to the left because that's going to go toward the other line. If I wanted to go down to the right, I certainly could, but it's not necessary on this problem to do that. It's wanting to glitch on me here and not actually do it where I want. So I'm going to have to restart that line for whatever reason. I've never had that happen before, so that's new. That time I didn't do a line at all. Oh my gosh. This is not wanting me to do this as well as I'd like. And this is also glitching on me moving it, but it's accurate enough now that I'm just going to go ahead and accept it and take the L on that one. Now the intersection is negative 5 comma 3 as the answer. Moving on to number 4 here. The top equation needs solved for y, but the bottom equation already is there. So the top equation, I'm going to subtract 3x and get 6y is equal to negative 3x minus 12. And then dividing everything by 6 yields y equals negative 1/2 x minus 2. So the slope is negative 1/2, and the b is negative 2. I'm going to go and graph that by starting at negative 2, or 2 down, and going up 1, left 2, up 1, left 2, and down 1, right 2. And I don't necessarily need to keep going over and over and over again for more points, although sometimes you may. But I'm doing it here because I have no idea how many points I'll need, and so I want to be better safe than sorry. Oh good, it wasn't glitching out on my point on this problem, which is convenient for me. So as I graph the other one, my slope is negative 1/2, and my b is negative 5. So I go down 5, and then in a downhill manner, I'm going to go up 1 over 2. And as we go through this and connect these, I notice, wait a second, these lines aren't going to ever touch because their slopes are the same. Remember, we said that when the slopes are the same, they're parallel. Now, I want to clarify, it's only if their slopes are the same and they have this different y-intercepts. If those were the same y-intercept, if this was also -5, for example, that means the orange line is in the same exact place as the blue line, which makes it infinitely many solutions or the same line. But the fact that they are different y-intercepts but still the same slope means that they are no solution because there's nowhere that they will ever intersect or cross. Now, if you notice that without graphing, good for you. You don't even have to graph as long as your work is short, or any work you should have. So number 5, top one is not quite by itself yet, so I'm going to divide everything by 2 and get y equals 4x plus 9. Turn to my slope is 4 over 1, and b is 9. So I'm going to go up 9. I'm going to go in an uphill manner, a rise of 4 and a run of 1. So that would be down to the left or up and to the right. And there's not really any room to go up and to the right. And I'm just going to keep going here. Down 4, left 1, or up 4, right 1. And so as I make all these points, I'm going to go ahead and connect them with a straight line. The other one, I'm going to go ahead and, in order to get to this by the y by itself, I'm going to subtract 24 from both sides and get for y equals x minus 24. I put that x first because I do need the y equals mx plus b, so the mx needs to come first. Dividing here by 4 on absolutely everything, we get y, we get this is secretly a 1, so it's 1x, or 1 over 4 times x minus 6. And our m is, oh, it glitched out there for some reason and deleted my 6. Oh, lovely. I get the slope is 1/4, and the b is -6, the y-intercept. And so I'll begin at b, and go down 6, and I'm going to go up 1 over 4 in an uphill manner, or down 1 left 4. And I noticed that I didn't really need to go up and to the right, because down to the left would be where the intersection would happen. And that intersection happens at -4, -7. Number 6, our last graphing example. This first equation, in order to get y by itself, I either multiply everything by -1 or divide everything by -1. And that yields y equals positive x plus 6. So the slope is 1 or 1 over 1, and the b is 6. So I'm going to go ahead and graph that. And connect all these dots. Oh, it's glitching out on me again. Hate to see it because I'm just slightly off of my line. 'Tis unfortunate. I've never had this happen before tonight, but that is okay. Tonight, as I'm making the video with the timestamp there, you can see. There we go. Now I'll do the other one where I have to divide everything by 3, but I notice that y is already on its own side compared to the x in the constant term. And I end up getting, as I flip it around as well, y equals x plus 6. So the slope here is 1 or 1 over 1, and the b is 6. And as I go to graph, I notice, wait a second, these are the same lines. The same b, the same y-intercept. These are the exact same lines. So this is IMS. They're going to intersect infinitely many times, a multitude of times here. And that's because not only do they have the same slope like they did in example 4, but however they have the same slope and the same y-intercept, the equations are exactly identical, although they appeared different at the beginning. But once I solved them both for y, got them in slope-intercept form, they truly were identical. Solving by substitution. So this is our second method today. This is one of our what we call algebraic methods. So rather than a visual example, we just do this all by hand and with pure math along the way. So our rules here are we're going to solve one equation for x or y. It doesn't really matter which one we pick, but there will be easier variables most of the time to pick. And then we're going to substitute whatever we get from solving the first variable by itself, solving for the first variable into the other equation of the two, because we're going to have two equations for each of these. And once we do that, we're going to solve for the remaining variable. Whatever, when we get to that point, we'll show it here in just a moment on example 7. And then once you find your first variable, whether it's x or y, depending on your problem, then we'll plug it back in to find the other variable, and that can be plugged into either equation. So, solving these by substitution. So notice each of these equations are already solved for y. Y is the only thing on that side of the equal sign in both these equations. And so what we can do, since we're saying y is or equals negative 7x minus 1, we're saying it's the same thing as that. Now, before, when we say y is the same thing as something else, so such as if I were to say y is 4, I could take this 4 and I could plug it in for y in the other equation. And so instead of y equals x minus 9, it's 4 equals x minus 9. And that's called substitution. I substituted 4 in for y. It's still doing all the same stuff y was doing before. It was on that side by itself. It was equal to the rest of it. And that would be called substitution, as I mentioned. And so similarly, we're going to substitute this entire thing, negative 7x minus 1, since that's equal to y, and we're going to put that in for y. And so we're going to rewrite the second equation, but except for y, we're going to write what y is equal to in the other equation, negative 7x minus 1. So we're going to put negative 7x minus 1 equals x minus 9, replacing that y on the left-hand side in this second equation with whatever y equaled in the first equation. And so here now we get an equation that we can solve. So I'd add 7x to each side, and I get negative 1 equals 8x minus 9. I add 9 in each of these, and I get 8 equals 8x. And dividing both sides by 8, I get x equals 1. And I do want to note that you could have plugged in the other direction. You could have taken this and plugged it in here, because y equals or is the same thing as x minus 9. And since it equals or is the same thing as it, we can replace it whenever we see it. And so I could plug that into the other y, and I would just get x minus 9 equals 7x minus 1. And we notice that it's just a flipped version of this equation, which means it's going to be identical as long as you solve it correctly. Now, we only have one variable, so we did step 1, 2, and 3. Step 1, we had to solve an equation for x or y. Here, it was already solved. Step 2, we substituted that was in the orange, into the other equation. Always has to be into the other equation. And then 3, we solved for that variable. We solved for x. And now we're going to substitute our answer into either original equation to find the other answer. So if you remember on our graphing ones we just did, that our answers were ordered pairs. There was an x and a y. So here we need the y value since we already have the x value. We always need both. And so I can plug it into either of these equations, whichever one I just happen to think might be easier to plug it into. And I'm just going to go ahead and plug it in the bottom one here, because I think it might be easier personally. But once again, if you want to pick the other equation, that's perfectly fine as well. And so now we have y equals 1 minus 9, which is y equals negative 8. And so now we're going to make an ordered pair out of this and call it 1 for the x value, negative 8 for the y value, and that's our answer, 1 comma negative 8. So on number 8 here, we have these two equations, and one of them has a variable by itself. It has y by itself, and y is or equals negative 5x plus 30. So I'm going to take that and I'm going to replace y from the other equation by what y equaled. Has to be from another equation. If you were to try to plug it back into this y, it ended up getting a false IMS, where it shows negative 5x plus 30 is equal to itself. Now, you can still get IMS here like we did with graphing, but that's not how it happens, where you plug it in to itself. So instead, we're going to plug in negative 5x plus 30 into the other equation for y. And so we're going to have 7x plus 3 times this entire quantity that y is equal to in your original equation. And so now we distribute the 3, and we get negative 15 x plus 90 equals 42. Then from there, I'm going to combine like terms to get negative 8x plus 90 equals 42. Subtracting 90 gets us negative 8x equals negative 48. And dividing by negative 8 yields or results in x equals 8. I shouldn't circle that yet, because I only have half my answer. Now that I found one variable, I need to go back and find the other variable, and I do that by plugging it into either equation, whichever one I think might be easier. And I'm going to choose this top one because 5 and 30 are smaller than 7 and 42, and 1 is smaller than 3 as well. And it's already solved for the variable I'm going to try and find. Since I already have x, I'm going to try to find the other variable, in this case, y. So I have y equals negative 5 times 8 plus 30. Negative 5 times 8 is negative 40 plus 30. Combining those to get y equals negative 10. And that gives me the order pair 8 comma negative 10. And a quick reminder, like we did for graphing, and we said, hey, that means that this is the ordered pair that would work for every single equation on this paper. That would be the case here. So if you ever want to volunteer for testing that out, feel more than welcome. Number 9 here. So I don't have any variable by itself, so I have to get a variable by itself. So here, I have some different picks I can make. Now, I would encourage you not to write down what I'm about to write down, okay? I'll let you know when you should start writing stuff down again. So let's just pretend here, or hypothetical, I should say, as far as which variable should get by itself. So let's play hypothetical. Let's get this first x by itself, the x in the top equation. So if I do that, I would be adding the 5y to start, and I would get 6x equals 5y minus 28. And then I'm dividing everything by 6, and we notice, wait a second, 5 doesn't divide by 6, and 28 doesn't divide by 6. And we're going to be left with a bunch of fractions. So that's probably not our ideal method, even though it would work. You always could do that. It's probably not our most ideal scenario. So let's say I were to try to say, oh, what if I solve for this y instead? Well, I'd be subtracting 6x to start. And so I'd get negative 5y equals negative 6x minus 28. And I go over and I say, oh, well, now I got to keep solving y by dividing by negative 5. And if I do that, once again, do I create nice, easy numbers to work with? No, I create a bunch of fractions, which we can do, but I think if we have the choice, we'd say probably not. So then I say, okay, what if I do the x in the bottom equation? And so I subtract y, and so I get 7x equals negative y plus 22, or you could do 22 plus a negative y. I just prefer having the variable first, personally, but you could have the positive number first here in this case, if you'd like. So we divide everything by 7, and while we certainly can do this, it creates a bunch of fractions, which once again, not our most ideal scenario. So let's say that we would instead, as I re-erase that to keep my arrow on the bottom, try and get this y by itself. And so then I subtract 7x to start, and I get y equals negative 7x plus 22, and I'm like, whoa! I already have my variable by itself. I didn't have to divide it all like I would have had to on any of these 3 other options. And I didn't create any fractions like I would have on the other 3 options. So this is a much better deal. So I definitely want to get that by itself compared to the others. So I would go ahead and pause the video and write this down here if I were you. Now, the kind of strategy there or the thought process you want to go through is saying, okay, which variable would be the easiest for me to solve for? And the answer is that if there's a variable that has a coefficient of positive 1, that's always your choice. If there's no variable with a coefficient of positive 1, then you want to pick a variable with a coefficient of negative 1. And if that's not an option available to you, then you'd want to pick something knowing that would divide into every other number in the equation if possible. Sometimes it won't be possible. We'll see that on a later example today. But for example, we know that we'd have to divide by whatever the coefficient was. We saw that on each of these three, that we'd have to divide by that number each time. And so, for example, if this was like a 2y, then this y would not be a bad choice because 2 divides into all three of these just fine. And so that wouldn't create any fractions. And so that would be a better option than 6, because 6 would not divide perfectly into those, even though 2 would. And so we always want to try and choose something that would divide into everything else. Once again, but our first option is if it's a positive 1y, positive coefficient of 1, or a negative 1 would be our second choice after that. So now that we have this equation by itself, or the equation with y by itself, I'm going to go and put what y equals into the other equation. Once again, I can't plug it into the same equation that I just solved for. I have to put it into the other equation for y. And so everything else is going to stay the same. It's going to be 6x minus 5 times y. But now y is different. It's negative 7x plus 22. And I put it in parentheses here because I have to distribute. And so now as I distribute this, I'm going to make this a plus and negative 5, so I ensure I take this negative with the 5 as I distribute, giving us positive 35x minus 110 equals negative 28. Combining those x's, I get 41x minus 110 equals negative 28. Then I will go ahead and add 110 to both sides and get 41x equals 82. Then at that point, I will go ahead and divide by 41, getting us x equals 2. So now that I have one variable by itself, I'm going to go ahead and plug it in and to either of the original two equations to solve for the other variable, the y. Now, this one looks slightly easier to me because it's a 1y and 22 and 7, or 22 is smaller than 28, and I don't have to multiply the x when I plug it in, I should say. Or sorry, I have to multiply the x when I plug in, but I don't have to divide by anything to get y by itself in this bottom equation, because it has a coefficient of positive 1. Now you could technically plug it into this equation that's already solved for y if you'd like. However, I recommend plugging it into one of the original equations rather than a modified version of one, just in case we made a mathematical error during our modifications when we solved for a variable. So I'm going to plug into that bottom equation like I mentioned, and do 7 times 2 plus y equals 22. 7 times 2 is 14. And I get 14 plus y equals 22. And then subtracting by 14 gives us y equals 8. And so that'll be the ordered pair, 2, 8 as our answer. On the number 10 here, so as I look at these four different options, these four different variables here, and I try and figure out which one should I get by itself, which one should I solve for, I look at this top left x and I say, oh, that's the one I want to pick because it's the coefficient of positive 1, where the others have coefficients that are very much so not positive 1 or even a negative 1. And so I'm going to pick that top left variable, the first x in the first equation, and I'm going to add 7y to both sides of that equation to get x equals 7y plus 53. Once again, I could choose the other ones, but they just would not be as easy because I create a bunch of division that I have to do, as well as potentially fractions, and on these ones very much so fractions, since not everything would divide by 4, for example, and the first one not everything would divide by 7, and the bottom one not everything would divide by 5. So now I take all of this that equals x, and I plug it into the other equation for x. Now notice in the first three problems we've done, we've always solved for y at this step in the dark green. But this time we solved for x, and so when I plug it in, I don't plug it in for y, I plug it in for x, because that's what it is. We only plug things in for what they're equal to, and so because it's equal to x, I plug it in for x. And so I have negative 4 times this whole parentheses, 7y plus 53 that we're plugging in, and then I can resume writing the rest of the equation, negative 5y equals 19. I distribute my negative 4, and I get negative 28y minus 212 minus 5y equals 19. Combining like terms gives me negative 33y minus 212 equals 19. Then if I add 212 to both sides, I get negative 33y equals 232. Sorry, try that again, 231. And so I divide both sides by negative 33. And I get y to be negative 7. Not quite done because I still have to find the x value for the ordered pair. And so I plug it into either of the original two equations. I'm going to plug it into the top one because x is already or has a coefficient of positive 1 here. But you can plug it into either equation that you so choose. X minus 7 times negative 7 equals 53. So negative 7 times negative 7 is x plus 49 equals 53. And subtracting 49 from each side gives us x equals 4, which results in the ordered pair 4 comma negative 7, 4 being the x value, negative 7 being the y value. Number 11 here, as I look for a variable to try and get by itself, I notice that, hey, this y up here doesn't have a coefficient of 1, but if I divide everything by 2, that would work, and y is already by itself now. Whereas in this equation, in the bottom, I'd have to subtract 3x and then divide everything by negative 1, or I'd have to add y and then move the 5 away. So there's a few more steps. There's an extra step in either of those scenarios for the bottom one. And so I'm just going to go ahead and divide this one by 2, even though there's one here that has a coefficient of negative 1. And realistically, it doesn't matter which one you solve for. We'll still end up getting the same results by the time we're all done. And even if we did solve for this x first or this x first, for example, even though we'd get some fractions and it'd be messy, you would still get the same answer at the end of the day for the xy coordinate, regardless of which one you use, assuming your math is correct. And so if I divide everything in this top equation by 2, I end up getting y equals 3x plus 5. And I'm going to take that and plug this 3x plus 5 into the y value for the other equation. So 3x minus, and then I'm going to put the parentheses, 3x plus 5 equals 5. That minus in parentheses is very important there. It comes from this, that we're subtracting the entirety of y. So when y is multiple things, we have to distribute this negative and change each of the signs inside the parentheses. Now, as I combine like terms, I get 3x and a negative 3x, giving us 0 x's, so I get negative 5 equals 5. That's an equation with no variables. Like we've covered before, when we had equations with no variables, we said, is this true or false? The answer here is false. Negative 5 is not 5, so there is no solution, which means, as we covered on our graphing section, that these are parallel lines. The lines that would have the same slope here. Now, if this was a true equation, such as 5 equals 5, instead of negative 5 equals 5, then we would call this IMS, which would mean that they're secretly the same line. Last but not least, number 12 here. As I try to get any variable by itself, I noticed that I would have to divide each coefficient with the variable at the end, but also none of these divide evenly by 5 or 7 in the top, and in the bottom, none of them divide evenly by 4 or 3. So I'm just going to go ahead and pick a variable and start solving for it. And in this case, I'm just going to go ahead and pick this x just because. So I'm going to add 3y to both sides and get 4x equals 3y minus 5. Divide everything by 4. And I get x equals 3/4 y minus 5 over 4. And now I'm going to take all of this, since it equals y, and plug it in for y in the other equation, and get 5x plus 7 times that entire thing I circled earlier, for that x equals 3/4 y. My apologies, I plugged this into the wrong part. I was supposed to plug that in for x, and I started plugging it in for y. Silly Mr. Kossel. So it goes right there, and we have 5 times that entire parentheses of 3/4 y minus 5/4 plus 7y equals negative 17. So I'll just continue on with the rest of the equation there. Now, as I try to handle this problem, I have to distribute the 5. And as I distribute the 5, I'm going to put that 5 over 1. And 5 and 4 don't cross-reduce. And so I multiply straight across and get 15 over 4y. Do the same thing here. Once again, 5 and 4 do not reduce, so I get negative 25 over 4 plus 7y equals negative 17. Now, as I combine like terms for my y's, I need common denominators. The 7 secretly divided by 1, and my common denominator here would be 4. So if I multiply the top and bottom of this fraction by 4, it becomes 28 over 4. Combining those gives me a positive and a positive, which add to make a bigger positive, 43 over 4y. Minus 25 over 4 equals negative 17. Now I know I'm going to have to be adding 25 over 4 here to both parts. And I also know that I'm going to need common denominators here. So I'm going to go ahead and work on that. And if I multiply the top and bottom by 4 here, I get common denominators of 4. I get negative 68 over 4, retaining this negative from right here. And so now as I combine like terms, I end up getting 43 over 4y, and on the across the top, negative 68 plus 25 would result in negative 43 over 4. And so now as I multiply by the reciprocal to undo the multiplication of this fraction, 4 over 43, the 43's reduce, the 4's reduce just how I wanted it to, and I get y. I do the same thing to the other side, 4 over 43. Once again, the 4's reduce, the 43's reduce, but this time you're left with a negative 1 on the top left. And so we get y equals negative 1 as our y value. And now we go back and find the x value. Now you can plug it into either of these original equations. I'm going to pick the bottom one since it has smaller numbers. And so that's going to be 4x minus 3 times negative 1 equals negative 5. Here we have negative 3 times negative 1 resulting in 4x plus 3 equals negative 5. Subtracting 3 gives us 4x equals negative 8. Then we divide by 4, and x equals negative 2. And so that results in the ordered pair of negative 2, comma, negative 1. So even though that problem has quite a bit of mess along the way with fractions, it ended up working out nicely, which sometimes it'll still end in fractions, but here we're thankful it didn't. And that'll do it for section 2.4, solving systems by graphing and substitution.